Hi, everyone. I thought I would record a video for you guys in case you want to learn a little bit more of the nuance behind injectivity and surjectivity to help you with some of those homework problems. So I have the definitions that were provided on the homework here, and I've also included some comments just about terminology. So injective is often called one-to-one. Surjective is also called onto. So maybe you've seen one-to-one and onto before. For whatever reason, we call it injective and surjective. And in this example, we'll be working with functions from the real numbers to the real numbers. In general, whenever I write something like this, the first set is called the domain, which you're probably familiar with. And to be precise, the second set is actually the codomain. Sometimes people will call this the range, but that's technically incorrect. We'll see why later. The range is actually a different thing, but no big deal. That's for the end of the quarter to worry about. For now, we just want to worry about injective, surjective. So the symbols are a bit of a mess. It says for all elements of my, for all pairs of elements in my domain, so any x1, x2 I pick, apparently if they have the same function value, then they must be the same number, is what that's saying. Maybe a better way to phrase it in English is f passes the horizontal line test. Maybe you don't immediately see why these are equivalent. That's fine. I'll show you in a second. It's also equivalent to phrase it slightly differently. And sometimes you will see it phrased this way, even in really rigorous texts. What I could do is I could take the contrapositive here and phrase it as x1 not equal to x2. So the negation of this conclusion on the right actually implies the negation of our assumption. And sometimes that definition is easier to swallow in the sense that it's saying, okay, if I give you two different x values, they better have different y values, which means your function does not do something like this. Right here, you would have, one x value giving you this y value, another x value giving you the same y value, and that would be a problem. Okay, so sometimes you see it that way. You won't hear horizontal line test used outside of like high school, but it's a good intro to the concept. All right, and then surjective says for all elements in my codomain, which I guess you can think of as the range for now, but it's really not correct. For all y values, there exists an x value mapping onto it. When I say mapping onto it, I mean f of x equals y. Okay, the shorthand for this is f attains all possible y values. So since we're talking about R, the real numbers, as our codomain, yeah, like any real number you pick, it will attain that value somewhere, meaning it should go from, negative infinity on the y-axis to positive infinity. It should go everywhere. All right, so those are our definitions. Those are our ways of thinking about them. What are some examples? Well, the homework asks you to come up with examples yourself. On the homework, you should write the actual definition of the function. Maybe I'll just draw some pictures here. So an example of an injective function, maybe something like this. That looks fine. That passes the horizontal line test, I could say. The horizontal line test meaning no matter what horizontal line I draw, it only crosses the function at most one time. Right, so that is an injective function. Oops. Something that's not injective, I don't know, maybe something like that. Let's try to draw it smoother. Not injective, because it fails the horizontal line test in many places. It doesn't matter if it passes it in some places. If it fails it anywhere, not injective. Right? So here we have, multiple crossings. That's like saying there are multiple x values mapping onto the same y value. That's a problem. That's sort of where the name 1-to-1 comes from. Here we have 3 things mapping onto one y value. That's 3-to-1. But you want 1-to-1. You want uniqueness, essentially. All right. Of course, these functions are more complicated than they need to be. You can come up with better examples, but just thought I'd get you used to the idea. Surjective, sure, let's do something wacky. Let's say I start at -infinity and then come up. Maybe I do some weird stuff. Let's draw that again. Yeah. You're allowed to do weird stuff for a surjective function, because here, any y value I pick, it does have an x value mapping onto it. Right here I have a ton. And in the case of surjectivity, that's okay. But this function would not be injective. But it's surjective, right? All you need to be onto is that every y value has at least one corresponding x value. This one, well, yeah. Every y value I could possibly pick has a corresponding x value. And what about not surjective? Well, there are a ton of ways to do that. Not surjective means, here, let me just erase some of this. Shouldn't have used dotted lines. Oh, well. Who cares? For not surjective, you have a ton of options. Maybe I'll just show one. This is kind of a weird example, but sure. What about a piecewise function that has a break in it? That would not be surjective, because this y value never gets attained. There's no x value producing that y value. Of course, you don't need piecewise functions, but works fine. So there you go. The idea of the homework is to write down actual function definitions, not just pictures. But pictures are probably a good place to get started. And you should try to justify why these statements in blue are true or false, and why. If you're trying to show one of them as false, make sure to negate it before you do so. Right. Negate it and then show why the negation is true. That's the same as showing it's false. The same as showing the original claim is false. All right, that's all. Thanks for watching. Hope you guys have, well, a good weekend whenever it comes around.